Hello everyone, welcome to Applied Chemistry Tutorials. Today we will talk about classification of polymers. So polymers can be classified depending on several parameters. The first type is types of repeating unit. Based on this, polymer can be divided in homopolymer and copolymer. The next parameter is mode of polymerization. Based on that, polymers are divided into addition and condensation polymer. Based on thermal response, like how the polymer is behaving under certain thermal condition, polymers are categorized into thermoplastic and thermoset. Then cost and volume produced, based on that, polymers can be commodity polymer and engineering polymer. All these four categories we have discussed in detail in our previous video. You can check that using this link here. Moving forward, the next parameter is origin. Based on that, polymers can be divided into natural polymer, synthetic polymer and semi-synthetic. Then based on physical property, polymers can be divided into three categories: rubber, plastic and fiber. Based on how the polymer chain structures are, polymers can be linear, branched and cross-linked. Depending on the configuration, polymers can be isotactic, syndiotactic and atactic. Then finally, based on crystallinity, polymer can be semi-crystalline and amorphous. All these five categories we will discuss in this video. Starting with origin, the natural polymers, these are obtained from natural sources such as plants and animals. Examples are natural rubber, cellulose, lignin, protein, silk, etc. Cellulose structure is provided here. Then synthetic polymer, these are man-made polymers synthetically produced from low molecular weight monomers. Examples are polyethylene, polystyrene, polyester, nylon, epoxy, phenylformaldehyde resin, etc. Polystyrene structure and nylon structures are provided here. Then the next category is semi-synthetic polymer. These are naturally derived polymers then modified artificially to improve the quality of the product. Examples are vulcanized rubber, cellulose nitrate, viscose rayon, etc. Cellulose undergoes nitration to produce cellulose nitrate using the mixture of sulfuric acid and nitric acid. Based on physical properties, polymer can be subdivided into rubber, plastic and fiber. Molecular cohesion is the main factor which is controlling the physical properties of these three different types of polymers. For rubber, polymer chains are held by weakest intermolecular forces leading to long-range elasticity. Rubber or elastomers has weak tensile strength, dimensional stability and undergo high elongation up to 1000% of its original length when stretched. Introduction of certain degree of cross-linking, which is popularly known as vulcanization process, helps the polymer chains to retract to its original position after stretching. Examples are natural rubber, synthetic rubber, etc. Then plastic, its intermolecular forces are in between rubber and fibers. It is more stronger than rubber and it also has higher tensile strength than rubber. Plastics can be linear polymer chains, soft, flexible and can be reshaped repeatedly upon heating and known as thermoplastic. Examples are polyethylene, polypropylene, polystyrene, etc. They also can be small molecules which can achieve three-dimensional network structure once cross-linked and become hard, rigid and cannot be remolded. This is known as thermoset. Examples are melamine formaldehyde, bakelite, etc. Now, for fiber, polymer chains have strongest intermolecular forces such as the hydrogen bonding. These are the forces working between the different functional groups which results in very high tensile strength. Fiber is thread-like woven in fabric, so used as textile material. Fiber has high crystallinity, sharp melting point. Examples are cotton, silk, nylon, polyethylene terephthalate, etc. So if we compare the tensile strength of these three material in the stress-strain curve, then for rubber its tensile strength is quite low but it can stretch a lot. For flexible plastic, it has comparatively higher tensile strength and it also has some stretchability. Now for fiber, you can see it has very high modulus, but it cannot stretch much. For rigid plastic, stretchability is very less, but it has very high strength. Moving forward, based on polymer chain structures, polymer can be divided into three different categories. The first one is linear polymers, which are made of linear sequence of bifunctional repeat units. Linear chains are closely packed, resulting high density, melting point and tensile strength. As you can see here, because of the regularity, they can pack very well in a crystal, which results in this properties: melting point, tensile strength very high. Example is high density polyethylene. Then branched polymers, these are linear polymers with short or long branches. Branches are side chains extending from the main backbone. You can see this is the backbone and these are the branches. Now degree of branching varies depending on polymerization process. These are less tightly packed, so lower density, tensile strength, melting point and readily soluble compared to linear counterpart. Because of this branching, they cannot pack very well in a crystal, so they are loosely packed, so they can be soluble very easily, and because of that their tensile strength, melting point, these are also low. Example is low density polyethylene. The next category is cross-linked polymers. These are network structured polymers. These are mostly linear chains chemically linked together via a process called curing, making the polymers of infinite molecular weight and insoluble. Cross-linked polymers are hard and rigid. Example is bakelite. The next category is configuration. When monosubstituted ethylene, example propylene, styrene, vinyl chloride, etc., polymerizes to form the polymer chain, it can attach via the following configurations. So assume this is the ethylene which is monosubstituted by X. Now for propylene, X is CH3, for styrene, X is C6H5, for vinyl chloride, it is Cl. Now if we assume this part as head and this part as tail, then when this monosubstituted ethylene polymerizes and make this long chain, then this link as head to tail. Again this link as head to tail. So this configuration is called head to tail configuration. The next one is head to head or tail to tail. And the third configuration is either head to tail or here head to head, here tail to tail. So this is a random configuration. So among these three configurations, the head to tail configuration is the most preferred one to avoid the static hindrance, because the substituent groups are equally spaced, so they won't repulse each other. So this is sterically preferred configuration. Depending on spatial disposition of substituents, polymer chains have another types of stereoregularity, which is known as tacticity. The first one is isotactic. For the isotactic polymer, all the substituents are placed on the same side of the main polymer backbone. So this one is the polymer backbone and X's are placed on the same side of this backbone. Now because of this regularity, they can pack very well in an ordered arrangement in a crystal, so they have high crystallinity. For the Syndiotactic polymer, this X or the substituent groups alternate from one side to another of the main polymer backbone. Now comes the Atactic. Now X groups are randomly placed across the polymer chain. Because of that, their crystallinity is very poor. Now the final category is crystallinity. When polymer melts or cool down, molecules reorient to crystallize. Polymer chains are very long and can fold back and forth to form lamellae. This is polymer lamellae. Multiple polymer molecules can be involved to make this lamellae. Several lamellae pack together to form spherical structure named as spherulite. In between the lamellae, there are usually disordered arrangements of chains known as amorphous zone. This can be visualized by using this theoretical fringed micelle model. So these are the ordered arrangements or lamellae. This forms the crystalline zone, and in between two lamellae you can see there are some disordered orientation which forms the amorphous zone. Then depending on molecular symmetry, substituent groups present and stereoregularity of the polymer chains, molecular packing may vary, which leads to different extent of crystallinity. Suppose if the substituent groups are bulky or the stereoregularity it is atactic type, then the polymer chains cannot be ordered properly, so its crystallinity will be low. Since polymers are very long chain molecules, perfect ordered arrangement is difficult to achieve. Degree of crystallinity for polymer usually varies in the range of 10 to 80%. So it is called as semi-crystalline material. Examples are polyethylene, nylon, etc. For few polymers, the crystallinity is close to 80 or very high. For few polymers, the crystallinity is pretty low. For few polymer, the chains are either very randomly coiled structure, example for natural rubber, or these are very rigid structure, example polystyrene, polymethyl methacrylate, and they cannot orient in ordered form upon cooling even under the room temperature. So these are known as amorphous polymer, and their degree of crystallinity is usually less than 10%. Okay, this is all for today's talk. For the next topic, we will discuss different molecular weights of polymer. Until then, please stay tuned with us, and if you like this video, please give it a thumbs up, share and subscribe. Thank you.